Hello, calculus students. In this lesson, I'm going to go over some of the common, not really methods, but common names and symbols that we use to indicate that you are dealing with a derivative. And if you want to print a sheet where you can follow along and fill in some blanks for note taking, you can go to bit.ly/d notation for derivative notation. So let's get some simple stuff out of the way first. In calculus, there are many different symbols that mean to or refer to the derivative. And in all of these examples, we will let y equal f of x be our original function. So let's look at a couple of the different notations we use, and they all have names based on who popularized it. So we will start with Euler's notation. Euler's notation is not one that we will use very often in AP calculus, but Euler's notation, if you want to find the derivative of the function f of x, use a capital D with a subscript x. That means x is your independent variable, and we're doing the derivative of the function f, or you could say the derivative with respect to x of the function y. There's also Lagrange's notation, which we will use quite frequently, and that's your common prime notation. So f prime of x, f prime, y prime of x, y prime. We'll use that one quite a bit. And we will probably never use Newton's notation after this video because it is kind of faded from popularity. But since he is fairly important when it comes to calculus, I thought I'd throw him a bone here. And he used a dot notation. So you put a little dot above the y. I really just put that in there just to have a little bit more of a complete list. So let's go on to one other. We won't use Newton's notation in my class. The one that I love the most is one called Leibniz notation, and it looks like this. So you would say df over dx, dy over dx, and sometimes it's just d over dx. And there is a difference between the dy dx, which is how I often say it. That's kind of a slang way of reading it, but dy dx, ddx, the difference between those two is that one is a command that means to find the derivative of whatever follows. The other one, dy dx, is the noun that means you are looking at the derivative. The derivative of the function is this. So the way we would use those two notations correctly is if you consider the function y equals 3x squared minus 5x, if I said d dx, and then in parentheses, I wrote 3x squared minus 5x like that, what that's doing is telling me that I need to find the derivative of 3x squared minus 5x. And the answer to that would be 6x minus 5. The noun, the derivative of the function is, would be written this way. So if y is equal to 3x squared minus 5x, then I could say dy dx is, and the derivative of that function y is 6x minus 5. So there's the two different notations. One of them is a command saying find the derivative of this thing. The other one is the noun, meaning we already have the derivative, and the derivative is this thing. Okay. Other points of emphasis with Leibniz notation, it's my favorite, so we're going to talk about it quite a bit here. The way you formally read it. Now, I've been saying dy dx, but the formal reading is the derivative of y with respect to x. That's how you read that formally. And the with respect to x part means that x is your independent variable. It's your primary variable. So anything that is not an x has to be given some type of special treatment. And a quick explanation of what I mean by that is let's consider the function, or the equation, I should say, y equals 3x squared plus 5z cubed. I am finding the derivative of y with respect to x. That means that x is my independent variable, and when you're doing the derivative of the independent variable, you just do your normal derivative. So the derivative of y with respect to x, well, the derivative of 3x squared is 6x. Nothing too tricky there. However, z is not an x. It's not that independent variable, and we'll still do the derivative normally first, but because z is not an x, it gets what I call the implicit treatment. But basically that just means you have to treat it specially, and what you would actually do with that is you would say the derivative of 5z cubed, well, it's 15z squared. That's not a z. It's 15z squared. But since that's not an x, we have to tack on this little special notation. We put a dz dx after it because z is not an x. And don't worry about the details of that. I'm just giving you a preview of what the dx means in the denominator. We'll deal more with that type of derivative later. Some benefits of Leibniz notation is it is very obvious, big, ugly. It's obnoxious. It's kind of like my mother-in-law. So it's a lot more in your face. So one thing we're going to do later in the year is something called implicit differentiation, which I kind of previewed with that Z example of there in part B. But we will start with equations like this, relations like this: x squared minus 3xy plus y squared equals 0. And our first step is going to be to find the derivative. And we could use the Euler's notation. I'm sorry, Lagrange's notation. But let's compare Lagrange to the Leibniz notation. Both of these are saying the exact same thing. It's our first step with the derivative would be 2x minus 3x y prime, or I could say 3x dy dx. And the reason I like the Leibniz notation is because the next step, once we do this step where we get this first pass at the derivative, our next step is we need to solve for the dy dx. We need to isolate that. And if you use the y prime notation, there's not a whole lot of difference between y and y prime. They look very, very similar. And depending on your writing, you might lose a y prime. It's very difficult to lose a dy dx. So I heavily prefer Leibniz notation because the derivative part of that, the dy dx, is very, very, very obvious. And then the last thing that is very good about Leibniz notation is it behaves just like any other fraction. And so in BC, we will get to a point where we do derivatives of parametric equations, where we will have the derivative of y with respect to t and the derivative of x with respect to t. And while this is a BC concept, we will use the same idea in other contexts with AB and in regular calculus. But if you divide dy dt by dx dt, well, think about algebra 1. What did you learn when you divide fractions? Well, you would multiply by the reciprocal of the denominator. This pen is not working the way it typically does. So I'm going to flip the denominator and say that's the same thing as dy dt times dt dx. And, well, when you're multiplying fractions, if you have the same thing on top and bottom, those can actually cancel, leaving you with the single fraction of dy dx. So the benefit of Leibniz notation is it also behaves like a typical fraction, which is very advantageous in context later on in the year. So let's go on to higher order derivatives, and we're going to go through the rest of these pretty quickly. Euler's notation. The second derivative is almost the same as the first, except it looks like an exponent. It's not an exponent, but you put a little superscript of whatever order you want. So the second derivative, you could even read it d squared of x with respect to x of f. And we're not going to use Euler's notation much. I do want to show it to you because it may show up in textbooks or on multiple choice questions or something like that. We will live on Lagrange and Leibniz for most of the year, and we'll never see the Newtonian, the Newton method. So there's Euler's notation. Lagrange would just be f double prime of x, f double prime, and that's one that I think we have seen already. Leibniz gets a little bit interesting. And kind of like Euler, we use the superscript of 2, but pay close attention to where those exponents are, especially with the noun version of it, the d squared y over dx squared. That is the correct placement of those 2's, and no, that is not the same as the first derivative squared. That does mean the second derivative, and the reason the exponents are in that location, and the best explanation I can give you is, well, we're finding the derivative of the derivative. So if I start with the first derivative, and then I'm going to command you, I want you to find the derivative of that derivative. Well, if you look across the top, I have two d's and a y, so d squared y. And if you look across the bottom, I have two entire dx's, so that would be dx squared. Now, I know in algebra, you're probably thinking, shouldn't that be the quantity dx squared? And algebraically, yes, but we don't put the parentheses around the dx. So there's a quick little explanation for why the exponents are where they are, and you need to know that that is the second derivative. So moving on, we're going to blitz this one, the third derivative. Euler's method is exactly what we would expect. You put a superscript of 3. Lagrange, you use 3 prime marks, and Leibniz, we'll use an exponent of 3 where there was a 2 for the second derivative. But sometimes we get into very, very high order derivatives. Some functions have cyclical derivatives, kind of like I has cyclical values when you raise it to different exponents. And Euler's notation is exactly what you would expect. If I want the 18th derivative, you just use an 18. Same thing with Leibniz. If I want the 18th derivative, you just use an 18. However, Lagrange gets a little bit cumbersome because if you want the 18th derivative, you don't want to have to write y 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's really cumbersome and inefficient. I suppose you could use tally marks 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. But again, that's not efficient. Some mathematicians will use Roman numerals in the place of the tick marks. However, the most common method we use with Lagrange's method to indicate higher order derivatives is you put the order derivative that you want in parentheses. Now, the parentheses are what separates it from being an exponent. So if I want the 18th derivative with Lagrange, you put an 18 in parentheses, and I'm going to put a little extra note here. Note, without the parentheses, f18 of x is the same thing as the function f of x to the 18th power. So those parentheses are what really distinguishes exponents from the order of the derivative. And this notation with Lagrange typically starts with the fourth derivative. So you'll use prime marks for first, second, third derivatives. But when you get to the fourth derivative, you usually will see f with a 4 in parentheses. And there is an explanation of your common derivative notations.